Hello, everyone. Welcome to a new edition of this Latin American webinar of physics. We're very excited to have as our guest today Professor Rodrigo Nemmen, who is a professor at the Universidade de Sao Paulo. Rodrigo got his PhD in physics at the Universidade Federal do Rio Grande do Sul, and after that he worked as a postdoc at different institutions, including the NASA, the Goddard NASA Center. And right now he's actually spending some sabbatical time at Stanford University. And he's going to talk today about exciting things with supermassive black holes and electromagnetic emission. So thank you for joining us today, Rodrigo. Before you take it away, let me remind everyone who is connected through the YouTube channel to please subscribe in all the other social networks like X or Facebook or Twitter. And please follow us in YouTube and subscribe to our mailing list so that you are up to date with the upcoming webinars. And remember that if you have any questions, please make sure that you write them in the chat on this YouTube channel. So thank you for joining us today. And now I'm going to give the space to Rodrigo. Thanks, Rodrigo.
Thank you, Walter. Thank you very much for the kind introduction. It's a pleasure to be here today talking about supermassive binary supermassive black holes. And I presume you can see my screen now. Yes?
Yes.
Okay, awesome. Yeah, so as I said, it's a great pleasure to be here today. And I want to tell you about supermassive binary black holes and more specifically, their electromagnetic counterparts. So let's begin by answering the question, what are exactly supermassive black hole binaries? So supermassive black hole binaries, they are, as the name says, they are a binary system composed of supermassive black holes with masses between 1 million and 1 billion solar masses. And they have, for astronomical standards, they have small separations between a fraction of a parsec to a few parsec. And what defines a supermassive black hole binary is that they are gravitationally bound. Okay, so with up to a few parsec separation. And if we included in the same scale the sun, we can see here, I'm showing that the arrow is pointing the sun in the same scale as a 100 million solar masses black hole here in this binary system. And we can see that basically the sun is smaller than a pixel in the screen. So we cannot see the sun in the screen because it's tiny compared to the scale of these vast systems. And how do we get this binary supermassive black hole systems formed? And let's begin with a story of structure formation, of cosmological structure formation. So all cosmological models of structure formation, they predict the following scenario for making a galaxy, a big galaxy. A big galaxy is formed from smaller galaxies. So here, according to basically all cosmological models of structure formation, we start from small galaxies, which are shown here with the arrow. And then through a sequence of mergers, these galaxies, they grow and grow and grow, and we get bigger galaxies out of smaller ones. So this is the idea from cosmology. And each galaxy, we know nowadays that each galaxy has a supermassive black hole inhabiting the center of each galaxy. So each galaxy, as they merge, they will bring her own supermassive black hole, and as they merge, They will bring the supermassive black holes together. And so, in fact, the cosmological models of structure formation, they predict a widespread population of supermassive binary black holes, because galaxies, they will merge, and their supermassive black holes, they will also merge, producing strong gravitational waves. And so this is a key prediction of cosmological models of structure formation, that there is a widespread population of supermassive binary black holes. And their mergers is actually a key way through which massive black holes, they grow. They grow via mergers and also via gas accretion. And so we expect to find supermassive binary black holes in the late stages of galaxy mergers, as I'm showing here. And why are these binary supermassive black hole systems important? They are key sources for gravitational wave astronomy. So here is a landscape of gravitational wave observatories ranging from lower frequencies, where we have pulsar timing arrays, where the periods of gravitational waves, they range from years going to a range of hours to seconds with space interferometers, as will be the case in the future with LISA. And then going to terrestrial interferometers, such as LIGO, Virgo, and CAGRA, where the wave periods, they are of the order of milliseconds or even smaller. And now when we show the range of strains expected here, supermassive binary black holes, they are expected to be the strongest gravitational wave sources for LISA, the Space Gravitational Wave Observatory, and also pulsar timing arrays. So they are key targets for these lower frequency gravitational wave observatories. But let me spend a bit more time talking about this fascinating pulsar timing arrays. So a pulsar timing array is this incredible idea where, by observing dozens of millisecond pulsars, which are pulsars which have a period of order of milliseconds. So the idea here is, by observing how the periods of millisecond pulsars scatter throughout the galaxy, they vary as a gravitational wave passes through, and comparing the periods of pulsars, these different pulsars scattered in our galaxy, we actually can use the whole galaxy as a gravitational wave observatory. And this is really a fascinating idea, which is implemented in these so-called pulsar timing arrays. And a long time ago, it was predicted that if there is a gravitational wave background affecting commonly all pulsars, so there is a background of gravitational waves shaking space-time everywhere. So there was this prediction that by making a plot of the background affecting each pulsar as a function of the separation of the pulsars on the sky, we would have a curve showing that if we ever saw a gravitational wave background in a pulsar timing array, it would show as a characteristic curve. And this is an awesome result released by the NanoGrav collaboration, which is a pulsar timing array observatory. With the 15-year data set of NanoGrav, we actually found, they actually found evidence for a gravitational wave background. And the money plot is shown here to the left. This is the so-called Hellingsdown correlation, which is a plot of the interpulsar color correlations as a function of the separation angle from 67 pulsars in our galaxy. And the surprising thing is that this gravitational wave background measured by the NanoGrav is consistent with many models of supermassive binary black holes. So we see a gravitational wave background. Nanograph sees a gravitational wave background, and this background is consistent with supermassive binary black holes. There were some surprises with the results. So, for instance, the amplitude of gravitational waves is a bit higher than expected from binary supermassive black holes. Okay, so this could imply that we have a bit more massive binary black hole mergers, or they are more frequent than previous models predicted. So this is the importance and motivation for this work, actually. We already have evidence for the presence of this binary supermassive black holes, confirming predictions of cosmological structure formation. However, not all things are easy. And studying supermassive binary black holes is notoriously difficult. And I will give here a few reasons why this field is quite challenging and quite difficult. So to begin with, even though these binary supermassive black holes, they are key predictions, detecting individual sources is quite tricky. And so this the way we find candidates for supermassive binary black holes is the following. We expect, so the idea here, once they have a low separations, the distance between the binary black holes is low, the period of the orbit is of the order of years. And so the hope is that there is some process which correlates with this period, and we would hope to observe if we see a light curve. In other words, if we see a time series of electromagnetic signals with our astronomical telescopes, and we see a period of the order of a couple of years or shorter, that could be due to the presence of a supermassive binary black hole. Maybe because this is correlated with the main period of the binary, or maybe the harmonics of the period. So this is the way we traditionally find candidates for supermassive binary black holes. So one of the best examples is the Blazer OJ287, where we found this source was monitored over basically a century. And we have found consistently periods in the source which are consistent with a smaller supermassive black hole orbiting a bigger black hole and punching through the accretion disk around the bigger supermassive black hole. This is another well-known example, the source PG1302, where we find evidence of periods in the light curve, which could be due to the presence of a binary supermassive black hole. And finally, this is a Fermi detected source. These are observations with the Fermi Large Area Telescope, and we also see a clear period here. The period in this case is of the order of 1 year and a half, if I'm not mistaken, over a 13 years span. And these periods, they could be attributed to Doppler boosting of radiation from the accretion disk, or the precession of the jets due to the influence of the binary. But the reason why these are not confirmed supermassive binary black holes is because usually we have several other explanations for the periods we see in the light curve, and these alternative explanations, you do not need a binary. You can always explain this periodical light curves with a single accreting supermassive black hole. Okay, so there is no confirmed supermassive binary black hole yet. And the other interesting thing is that this is especially interesting for theorists, is that supermassive binary black holes, they are pretty hard from a theoretical point of view to model. And so one important difference between the supermassive binary black holes and the stellar mass black holes observed by LIGO, Virgo, and Cagra is that the supermassive binaries, they are in gas-rich environments, okay? So we cannot neglect the effects of gas and magnetic fields for the supermassive binaries. This is a key difference between the supermassive versus the stellar binary systems. So they are pretty hard to model, the supermassive ones, because number one, we need to take into account a dynamical space-time of the two black holes orbiting each other and bending space-time as they move. We also have to take into account, as I mentioned, because they live in gas-rich environments in the centers of galaxies and merged galaxies, we have to take into account gas. In other words, the accretion disk around the source. And we have to take into account magnetic fields, because the accretion disk brings in magnetic fields from far away, or boosts the magnetic field via dynamo processes. So magnetic fields are a key ingredient. And finally, radiation, because there is a lot of dissipation in this gas-rich systems, and they produce a lot of radiation. So when you incorporate all these ingredients, all these 4 ingredients, you have a pretty tough system to model from a theoretical point of view. And the accretion processes in supermassive binary black holes, they are way harder to understand than the accretion going on in single active galactic nuclei. There is lots of unexplored territory here, and lots of potential for theoretical investigations and modeling. So in fact, there have been a lot of simulations that are being carried out. There are lots of simulations of the supermassive binary black holes underway, with varying degrees of computational complexity and varying degrees of the physics involved. And here I will show you only one of such simulations. So this is a simulation performed by Dascoli and Scott Noble, and this was visualized by NASA by the experts at NASA Goddard Space Flight Center. So this particular simulation I'm showing you here is a general relativistic magnetohydrodynamic simulation. There is no, as far as I know, there is no numerical relativity here. They are not solving the Einstein equation. They are using tricks to model the event horizons of the two black holes. There is MHD involved. There's plasma and magnetic fields. And in this GR-MHD simulation, we already see some of the common features of such systems emerging from these numerical simulations. So number one, we can see the circumbinary disk. There is a low cavity density on which the binary black hole is orbiting, okay? So the binary is torquing the gas, it's transferring angular momentum to the gas. So as a consequence of this, the binary creates a low density cavity. And outside this cavity, there is a circumbinary accretion disk. We see also lumps of gas flowing into the binary, and each of the supermassive black holes has a mini disk, okay, a mini accretion disk around each supermassive black holes. This is usually a common feature of such simulations. The mini disks may or may not survive throughout the late stages of the merger. This is under debate. Here, there are magnetic fields as well. So there are many such simulations underway, different degrees of complexity, and it's a fascinating field of study. However, and I should stress this, the electromagnetic counterparts of supermassive binary black holes, they are entirely unknown, okay? So this raises a question of whether we even expect to localize these gravitational wave sources in the future with electromagnetic follow-up. We simply do not know what sort of electromagnetic counterparts we should observe from such systems. This is an active field of research to understand these counterparts. And this is quite timely, actually, because there are several upcoming wide field electromagnetic observatories. And to name just two examples, we have the Rubin Observatory, formerly known as the LSST. We also have the SKA in radio. So it's pretty timely that to better understand, to advance our understanding of the electromagnetic counterparts of supermassive binary black holes. And this brings us to our work, to this work. So the central problem of this work is the following. Imagine you have a point source of radiation, and you cannot resolve the source. And how to tell whether this point source is one single active galactic nucleus, one AGN, one supermassive black hole, or how to tell whether this is actually two accreting supermassive black holes in a binary system. Okay. And this is quite a challenge if you cannot resolve the system, and if you do not have access yet to the gravitational waves from this system. And we want to know whether the system, we want to know, just by observing the electromagnetic signal for the system, we want to know whether this is a binary system or just one supermassive black hole. So we need predictions for multi-messenger detection. So we need predictions for the electromagnetic signal that will come together with the gravitational wave. And in this work, I am predicting that these systems, they should produce a unique EM signal from these systems. So leading to the merger, these systems, they should produce an ultra long electromagnetic burst just before they merge. And this is basically the key result from this presentation. And this is the central problem and the key result from this presentation. And now I will walk you through how to arrive at this prediction of this electromagnetic counterpart from supermassive binary black holes. So let's begin by asking the question, what happens when you have an accreting supermassive binary black hole? So what happens when you have an accreting supermassive binary black hole? So our story begins in the gravitational wave-driven spiral regime, as I'm showing here in this slide. In orange, we have the accretion disk. Let's imagine that we have two supermassive black holes that they were brought in close together because of a merger of two galaxies. Now we have these two supermassive black holes. They are orbiting in a gas-rich environment inside an accretion disk. And here, the scenario I will show combines ideas of accretion theory. They are basic ideas of accretion physics and gravitational physics, and they will lead to the following scenario. So number one, in this gravitational wave-driven regime, because of the torques of the binary system, they will create a low-density cavity, as I mentioned before, okay? And so they will be orbiting inside this low-density cavity, outside of which is the circumbinary disk. The binary carves a cavity in the disk, and this becomes a circumbinary disk. This is pretty uncontroversial element of this model. The radius of the cavity is twice the binary separation, usually as a result of this binary torques. And as the binary orbits, with the binary orbit, there are two relevant time scales that are competing here. One time scale is due to the shear stress in the circumbinary disk, in the dissipation of angular momentum in the circumbinary disk. This is the viscosity time scale. And the other time scale is the dynamical time scale associated with the orbit itself, which will actually get shorter and shorter as the binary advances because it's releasing gravitational waves. So as the system loses energy by gravitational waves, the system will get closer together. This gravitational wave time scale will actually get shorter and shorter and shorter. So these are the two competing time scales here, the shear, the viscosity time scale, and the gravitational wave time scale. So as the system is losing energy, the binary is getting closer and closer, and the disk is catching up. It's losing angular, the accretion disk is losing angular momentum because of shear stress, and the disk is catching up to the binary because the two time scales are actually comparable. However, at a critical distance, when the binary gets at a specific distance, which in this case is of the order of 10 gravitational radii, what happens here is that the gravitational wave timescales gets shorter than the viscosity timescale, and the binary quickly merges because of this. It catastrophically loses energy because of the gravitational waves, and the binary quickly merges together, leaving the accretion disk behind. And then only afterward, the disk will eventually catch up, flow down to the innermost stable circular orbit, and continue accreting onto the newly formed, the newborn Kerr black hole, which is the product of the merger of the two binary black holes. Okay, and this is the basic picture that I will consider here in the model for the electromagnetic counterpart. Okay, they're combining ideas of accretion theory, accretion physics, and gravitational physics. Now, if you are the kind of person that asks in astronomy talks, what about magnetic fields, you are going to love what I will talk about next. So what about magnetic fields? And so magnetic fields are pretty important here because in any accretion disk, we have a lot of magnetic fields in the accretion process itself, because of the accretion process itself. And so we expect the low density cavity of the binary supermassive black hole to be filled with a B, filled with magnetic fields. And as the cavity shrinks because the binary is merging, the cavity will actually squeeze together the magnetic fields. So as the binary merges, as the binary approaches and the cavity gets smaller and smaller and squeezes the magnetic field, the B strength will go up as time advances here. B will increase in strength. So the key question that we should be asking ourselves here, and when we think of a supermassive binary black hole merging after a galaxy merger in a gas-rich environment where we have an accretion disk, where we have magnetic fields, the question is, what happens when the binary interacts with the magnetic field here that is populated by the accretion process? So let's investigate what happens when a binary interacts with the magnetic field. So let's consider here, so in blue, I'm showing the magnetic field lines for illustration. And let's push, for simplicity, let's push not a Kerr black hole. Let's consider, for simplicity, a Schwarzschild black hole moving through a uniform magnetic field line as moving through uniform distribution of magnetic fields here, as I'm showing here. So as a black hole moves across a magnetic field, something pretty interesting happens, because we can model the event horizon as a perfect conductor. Okay, this is a result of investigation many decades ago, that we can essentially model event horizons as a perfect conductor. And so we can actually reframe this question as, what happens when you have a pretty big spherical conductor moving through a uniform magnetic field? And what happens here is that we will get an EMF. We will get a motional EMF out of this process. Okay, and to understand what happens when you have a binary system moving, orbiting inside a magnetic field, we can basically apply the good old college introductory physics law, the physics from introductory physics in college, Faraday's law. Okay, and Faraday's law, which is what you want to apply when you want to understand what happens when you have a conductor moving through a magnetic field. Faraday's law predicts there will be an EMF out of this, and the EMF is given by this expression, which is a product of the velocity of the binaries, the orbital velocity, the magnetic field in the cavity, and the size of your conductor, which in this case is the radius of the event horizon. And in addition to the EMF, it will have also power dissipated in this. It will have a power produced by the orbit, purely by the orbit of the binary inside the magnetic field, which is given by the square of the EMF. And so this is the square of the orbital velocity times the square of the magnetic field in the cavity times the mass of the system. So we can notice something pretty interesting that will happen here as time advances. Notice that as the binary approaches the merger, the velocities will go up dramatically. They will actually approach the speed, the velocity of light. So as time advances, V will go dramatically up. Because the cavity will decrease in size, B will go up dramatically as well. So the power dissipated out of this system, purely because of Faraday's law, will dramatically go to the square, to the product of two square quantities, up dramatically. So I did the calculations out of this, and now I will show you some results that come from basically solving this predicting what comes out of this equation of this power as a function of time. So let's see some predictions out of a typical binary supermassive black hole in a cavity inside a circumbinary disk. So here I will show you predictions for considering that the two black holes that have each black hole has a mass of 100 million solar masses. So in this plot, X is the time in hours, considering the masses of the two supermassive black holes. Y is the electromagnetic power that is coming out of the system because of the orbital motion. The merger will happen at t equals 0. By definition, the merger is at t equals 0 here in this plot. So the prediction from this model is that at first, and okay, so one important thing to mention here is that I'm considering that both black holes, they are Schwarzschild black holes, number one. And number two, there are no mini disks here. If there are mini disks, we need to add more physics. There will be a whole background emission that we have to add on top of this. This is basically the 0th order prediction of this model for Schwarzschild, when both black holes are Schwarzschild and neglecting mini disks. So first we start with the system will start as an inactive, what looks like an inactive galaxy or a low luminosity AGN. As the binary system advances towards merger, we have a power being produced purely by the orbit, and we expect actually outflows of electromagnetic radiation and actually gas out of this system. So we see here that the system increases in brightness by over 3 orders of magnitude, transitioning from an inactive or low luminosity AGN up to a quasar. And then the binary black holes, they will merge into a single curved black hole with a given spin. We have the ring down happening over a light crossing time scale across the horizon. Then we will have one single black hole. And as the disk then catches up with the new curved black hole, remember the disk was left behind. And I forgot to say, when the accretion disk decouples from the binary, when the binary is merging too fast for the accretion disk to merge, we call that decoupling, okay? So after decoupling, the disk will slowly fill in the cavity, okay? B will go up and we'll have this characteristic increasing curve here. And eventually we will have the per supermassive black hole happily accreting matter from the accretion disk with a jet. We will have, in the first part of this model, we have an outflow powered by purely the orbit of the binary supermassive black hole. And in the third and fourth part, we have outflow powered by what we call the Blandford-Nagic process. It's powered by the spin of the single curved black hole. And here is a comparison of a scenario in orange, taking into account the decoupling between the accretion disk and the binary, and in blue, not taking into without any decoupling. And we can see here that a typical prediction of this model is that we have an ultra long burst of electromagnetic radiation that will start being produced right before the merger itself. This ultra long burst, it can last several hours. The duration will depend on the masses of the supermassive black holes. And because of this ultra long burst, it will make a previously inactive galaxy become a quasar and then fade again into quiescence into a low luminosity AGN. Now, what I'll do here, I will zoom in the half an hour before the merger and the half an hour after the merger. And here, again, comparing the two predictions, one with the coupling and the other turning off the coupling between the accretion disk and the supermassive black hole. And the dotted line is showing here the gravitational wave time series, which here I scale the gravitational wave signal to match the power in electromagnetic waves. And we can see here that there is a very strong correlation actually between the gravitational waves and the electromagnetic power predicted in this model. So we expect that the power that will come out in light is pretty much correlated with the gravitational waves. And this is a pretty important prediction because it is telling us that we should be able to follow up the merger of this system, this sort of systems with our traditional astronomical observatories, and perhaps we will be able to easily. Easy. That's up to what is easy is actually pretty hard when you do it in practice with the telescopes. But we should be able to follow up and localize the systems after they merge. When we have the triggers from the gravitational wave observatories, this model is telling us that potentially we will be able to follow up and localize with our conventional astronomical telescope this supermassive binary black holes when they merge. So there are many implications that come out of these calculations. So the first implication, as I mentioned, we expect a strong correlation between the electromagnetic signal and the gravitational waves pre-merger. This model is suggesting that we should be able, as I mentioned, to pinpoint the host galaxy with multi-messenger observations. And the other prediction is that the light curve is sensitive to both binary and accretion parameters. So by following up the system and feeding the light curve with this model, we should be able to constrain the mass. We should be able to potentially constrain the spin of the newly born black hole, the coupling, the accretion rate, and the magnetic field. All of this with the light curve monitoring. And there's much left to be done, actually, to get the calculations right. So in conclusion, now finishing up and with a summary of what I presented here, the key takeaways from this presentation is that supermassive binary black holes, they are extremely important sources for future gravitational wave observatories and current pulsar timing arrays. However, they lack a unique electromagnetic identification, and this is the central problem that this work is tackling here. And with my calculations, I'm predicting that these systems should produce an ultra-long electromagnetic burst lasting of the order of hours before the merger. We will probably see this in radio, optical, and also other wavelengths, like probably in X-rays as well. There should be a dramatic changes where this newly formed galaxy, the late stages of merger, it will change from an inactive to a quasar down to back to a low luminosity AGN in a couple of hours before the merger, through the binary merger, and then afterwards, after you have the newly formed Kerr black hole. The model predicts a strong correlation between light and gravitational wave emissions. So in other words, we should be able to pinpoint the host galaxy once we have the gravitational wave observation. And we should be able to constrain the relevant parameters of the system by combining the gravitational waves with the electromagnetic observations. And that's all for today. Thank you very much for watching, and stay tuned.
Excellent. Thank you very much, Rodrigo, for this very interesting talk. Before we read some questions that have arrived to us, I want to ask if there is any question from the people in the meeting.
Yeah, I have a question for Rodrigo. Rodrigo, very nice the webinar, very interesting. So I was wondering, because I mean, your talk was about the electromagnetic emission from the binary, but because when you were mentioning about the magnetic fields of with the accretion disk and all the interaction, should this kind of system be also efficient to accelerate the cosmic rays or some other type of? I mean, and since this type of systems are quite, I mean, they are everywhere, kind of would be a contribution for the cosmic spectrum or something like that. I mean, I don't know if it is too off the topic, but yeah, that's the question.
That's a great question, actually. That's a great question. It's not off topic, and I did so. The model that I presented is a toy model, basically. As you probably noticed, it's a very, very broad model considering the basic physics of the system. So this fancy computational simulations that I show, they are pretty computationally expensive, and you can run just a few models. With the latest models, you can run just a few experiments. This is the basic physics, so we can understand better what's happening there. And yes, I do expect that there will be vigorous particle acceleration and hadronic processes, hadronic accelerations, and as a consequence, cosmic rays and neutrinos. Now, whether we see gamma rays as well, that's another question. Depends, of course, on the. I'm not sure we will see gamma rays because of the gamma ray opacity, because of the large photon field here and pair production. But the thing is, other things that I did not consider in this toy model is you will have this low density cavity with collisionless plasma in the collisionless regime. Also, the magnetic field will not stay perfectly organized as I show there. So I expect that there will be some chaos, literal chaos happening there with also reconnection. So you have a localized reconnections happening there with particle acceleration. One thing that I didn't really touch this, but this is in the upcoming paper that I'm writing, is that you expect jets coming out of each black hole and a big isotropic electromagnetic outflow. Okay, and I can't tell you yet exactly how the radiation will show up, radio, optical, X-rays, because I need to model how this Poynting flux is transferred to charged particles. And that part I'm not putting in the model. The model is giving you just a broad amount of EM power coming out of the system. But depending on how this is transferred to particles, you will see all sorts of different electromagnetic wavelengths, and certainly X-rays. I expect jets from the system, and cosmic rays and neutrinos.
Okay, thank you.
Right, excellent. I have a question for Rodrigo, and then I can read a couple that we have here from other people. Every now and then, and especially a few years ago, we see papers where people have measured at redshift equal to 4 or 7 supermassive black holes in AGN that have masses larger than 10 to the 9 solar masses. And then people go crazy because the standard formation of the seeds for these supermassive black holes, they don't agree, or their intention with these huge masses. Then people start talking about maybe superadding to an accretion, or then they start adding dark matter or other things, like trying to explain this. Could this merging of supermassive black holes at some point be a mechanism to explain these huge masses for AGN at this late redshifts?
Mm-hmm. Yeah, no, there is a lot of this is the point you touched upon, is a vigorous area of study, of course, especially with the James Webb possibly constraining the properties of galaxies and the sites of seed supermassive black holes in the faraway universe, of course. So this is a vigorous area. One thing I can tell you is that it looks like and this is actually from old calculations from 20 years ago. There have been more recent calculations, but the pioneering work is from 20 years ago, from semi-analytical calculations, from plugging in black hole growth recipes with merger trees, dark matter merger trees, and then this has been refined with the cosmological simulations. So one common aspect of these calculations is that the main growth channel of supermassive, the main growth channel of massive black holes is accretion. Okay, it's accretion. It's not so binary. The mergers are important. Okay, but the main growth channel is accretion. Okay, that's what I can tell you.
All right, thank you. We have a question that arrived through our internal channels. It says, can you please comment on why you think you can disentangle the astro from the binary dynamics parameters from the light curve? Would it not be super degenerate?
Oh. I expect, yeah. So I expect quite some degeneracy there. In order to answer your question, I will need to do an assessment. Like I will have to basically do some simulations with this model to actually produce some mock data, and then do some and I will need to do actually simulations to judge the amount of degeneracy from the posteriors. So yes, you do have a point. There will be some important level of degeneracy, and I'm trying to see if my intuition tells me the worst parameters here, the most degenerate parameters. Well, from the duration, if we, well, I hope we observe this system. If we don't, if we never observe such an ultra long burst from mergers, then the model will be killed, of course, which is this is how science advances, by killing theories that did not work. But if we observe such a system, certainly the duration of the burst will tell us about the mass. So I think the mass will be the last. My intuition tells me that the mass will be the easiest parameter to constrain. Now the hard one will be spin of the newly formed curved black hole, because there are many uncertainties in this series of jet formation. You know, Blandford-Snark. The second part comes from Blandford-Snark. Accretion rate will be pretty. There will be some level of degeneracy as well. Mass ratio. Okay, so the mass ratio will be a pretty tough parameter to measure here. Oh yeah. So that's it. Yeah, thank you for your question.
Right, thank you. And there is another question. It says, can these binaries start with a, I mean, I guess this is the part where you were showing how the process starts. Can these binaries start with a common jet, a la Blandford pane?
Yeah, they can. They certainly can. And this is something, so as I mentioned, I did not consider mini disks. So if we have it all depends on how. So one thing from force-free numerical relativity simulations. Okay, so you have magnetic fields and you have the binary black holes and numerical relativity. One lesson is that even if there is no gas, if there is no accretion happening, you still expect jets coming out of the jets powered by orbit. It's like an orbit, and it's something which is analogous to the Blandford-Snark jets, but powered by orbit. So we do expect jets coming from each black hole, BZ-like jets, okay? But we also expect that these jets should be subluminous compared to an isotropic Poynting flux component, which should be way more important than the jets. And if you add the mini disks, it depends on how vigorous are the mini disks. The simulations predict different things. I did not incorporate mini disks. It all depends on how big is the accretion rate on the mini disks, and also the spin of the black holes, which I did not. I considered them Schwarzschild black holes. But depending on the actual parameters, the process I'm modeling here could be dominant. But if they are spinning very fast and the accretion rates are if the accretion rates are non-negligible, and by non-negligible I mean 10% of Eddington, big spins, the process I'm showing could be comparable or perhaps subdominant. We will need to do the calculations.
All right, thank you, Rodrigo. Any questions from Roberto or John? All right, and then I have one more here. How can the light curve of the accretion change so much by one black hole punching the accretion structure? And what is the typical size of the accretion disk with respect to the size of the black hole?
So one clarification here: the light curve is not changing because the black hole is punching the accretion disk. This is a result of the black holes moving through a magnetic field that was put in place there due to the accretion process. Okay. So the other question is, what's the size of the? I think the other question was the size of the accretion disk compared to the black hole, the binary system. I don't know. The question is not relevant. I mean, because of my answer, you see that the question is not really relevant. But in any case, the accretion disk should be of the order of 10,000 or 100,000 times bigger than the event horizon radius, more or less.
Great. Thank you, Rodrigo. All right. Is there any other question in the room? If not, let's thank Rodrigo again for this very interesting and beautiful talk. To everyone who is watching on YouTube, please make sure to subscribe to this channel so that you are up to date with the upcoming webinars, and also follow us on YouTube. There is a comment on the YouTube channel by Jos Incarnate saying thanks for a great talk. Thanks, really good. And we hope to see you all in the next webinars. And I hope that you have a nice rest of the week. Thank you, Rodrigo, and we'll see you all later.